Hi everyone, and welcome to the ICIP tutorial on multitask image and video compression. My name is Ivan Bajic and I'm with Simon Fraser University in Canada. Before we begin, I'd like to thank ICIP tutorial chairs Jean and Nelly for inviting me to present this tutorial. I would also like to thank my former and current students and collaborators in the SFU Multimedia Lab whose work has contributed to this tutorial. Thank you. We will start the tutorial by defining what we mean by multitask compression and what potential benefits it may have over conventional single-task compression. We will also talk about the history of the problems related to multitask compression and mention some of the current applications that require multitask compression. Then maybe we'll move on to the theory, where we will first review the relevant concepts from information theory, such as mutual information, data processing inequality, and rate distortion function, and we'll use those concepts to derive some bounds on feature compressibility. We will also talk about bit allocation in multitask coding. Following that, we will move on to the current research and practice in multitask compression. And specifically, we will talk about some of the recent literature on multitask image coding and multitask video coding. And we'll conclude this section by discussing privacy in multitask compression. And finally, we'll conclude the tutorial with a brief overview of the standardization efforts related to multitask compression, namely JPEG AI and MPEG VCM. Video coding for machines. So let's get started. So what do we mean by multitask compression? Most image and video codecs we use today work as follows. They take an input image or video and code it into a compressed bit stream and then decode it to reconstruct the input as accurately as possible. We can consider this to be a default task in image and video coding, namely reconstruction of the input at the same resolution, bit depth, and so on, as accurately as possible in terms of some distortion metric. But we may want to do other things with the encoded bitstream. For example, we may want to be able to decode the input at a different resolution or bit depth. Or we may want to be able to perform some analysis of the input, such as, for example, classify the input image or detect objects in it. So multitask compression is a way of encoding the input in such a way that efficient execution of multiple tasks is made possible. So one could ask, why don't we simply perform the default task, which is reconstructing the input image or video as accurately as possible, and then run any further task such as post-processing or analysis on that reconstructed input. Indeed, this is possible, and this is how things are done now. Most post-processing or analysis is being done on images and videos that were reconstructed from some compressed representation. However, multitask compression can bring several key benefits to the existing practice. For example, it can offer reduced complexity because task-specific decoding may be simpler than default task decoding plus post-processing or analysis. Another benefit is avoiding input reconstruction. This could reduce memory requirements, and it could also improve privacy because the input image or video wouldn't need to be reconstructed. And finally, and possibly the key benefit, is that most tasks can be performed at a lower bit rate than what would be needed to achieve a good, highly accurate reconstruction of the input. Although multitask compression may seem like a new topic, in the history of compression, there are actually multiple streams related to it. Two examples are scalable coding and compressed domain analysis. So in scalable coding, the goal is to encode the source in a way that allows multiple decoding options, such as to support different quality levels, resolutions, or frame rates of the encoded input. Whereas in compressed domain analysis, we start with the conventional single task bitstream, or sometimes a scalable bitstream, and then decode as needed to support a specific task without reconstructing the input. One of the earliest examples of scalable coding is the Laplacian pyramid by Burton Adelson, which was published in the IEEE Transactions on Communications in 1983. This was before wavelets or subband image coding. The authors define a Gaussian pyramid that contains a multi-resolution representation of the input image, where level 0 is the input image at the original resolution, level 1 is the image at a lower resolution, and so on down to some very low resolution. Then Laplacian pyramid is defined as the set of differences between a low resolution image upsampled to the next higher resolution level and the difference taken from the image at that level. So these Laplacian planes are then quantized and encoded. At the decoder, depending on how many Laplacian planes you decode and reconstruct, you can obtain the decoded image at the given resolution, one of those that existed in the original Gaussian pyramid. This paper has inspired many subsequent works on multi-resolution compression, and in some sense has led to what we subsequently knew as subband and wavelet image and video coding. Fast forward a couple of decades and we have JPEG 2000, an image coding standard supporting various forms of scalability. It is built upon the subband or wavelet transform, which is more efficient than the Laplacian pyramid, and just like Laplacian pyramid, supports resolution scalability. Other coding tools within the JPEG 2000 standard allow for quality scalability, where the image could be decoded at various qualities, as well as region of interest coding or decoding, where different parts of an image could be decoded at varying qualities. Scalable coding has also been developed for video compression. One example is scalable extension of H.264. Here, the base layer, which is shown as layer 0 in the figure, encodes the video at the lowest resolution, quality, and frame rate. Subsequent enhancement layers provide the necessary information for higher resolutions or frame rates or qualities. At the decoder, only the layers needed for a particular rendering requirement have to be decoded. Another example of scalable video coding is object-based coding in MPEG-4. Here, it is assumed that the scene is segmented into multiple video objects, and each object is encoded into its own video object plane. At the decoder, these video object planes can be decoded and composited to create a composite scene. Since there are many combinations in which these objects can be combined, we see that multiple versions of the input scene can be decoded from the same bitstream. So this also represents a multitask coding system. To summarize, we can say that scalable coding is a form of multitask coding, but all tasks that have been traditionally considered are related to rendering. They relate to changing the resolution or frame rate or quality, or compositing a scene out of multiple objects. There are no real analysis tasks here. Although object-based coding relies on external analysis to tell it what the objects are, the task itself is compositing a scene out of those objects. So, in that sense, previous forms of scalable coding don't really consider the full spectrum of tasks that we may be interested in doing now. The other stream of research related to multitask compression is the so-called compressed domain analysis. But what is compressed domain? If we look at a typical compression pipeline, we'll see that the input image or video is first subject to various forms of prediction or transforms, followed by quantization, followed by entropy coding. The output of the entropy encoder is the compressed bit stream. That's the compressed file, and in a strict sense, that is what compressed domain is. However, it is very difficult to analyze variable length coded data, and so most papers that talk about compressed domain analysis in fact consider data that's been entropy decoded. And perhaps more appropriately, that type of analysis could be called transform domain analysis. So the true compressed domain analysis means analyzing the compressed bit stream without entropy decoding. This is very difficult, as mentioned earlier. Part of the reason is that the compressed bit stream looks like IID binary noise. The bits are equally likely and seemingly independent of each other. So there's very little you can say about the content if you just look at those bits. That's part of the reason why there are very few papers on this topic. However, it's still possible to perform some analysis or inference on the compressed bit stream if auxiliary information is available or if the bit stream has some special structure. One example is visual saliency estimation in H.264 bit streams. This type of analysis relies on being able to tell how many bits are used per block to encode a given frame. This is called operational block description length, or OBDL for short. And using this information, together with some post-processing, it is possible to predict visual saliency. So the image at the top left shows the heat map composed of human gaze locations and overlaid on top of the corresponding video frame. The next image is the prediction of visual saliency made using this OBDL approach. And the other images show the predictions of visual saliency obtained by other state-of-the-art methods at the time. And as you can see, OBDL can do quite a good job of predicting human visual saliency, and it does so without even entropy decoding the bit stream, just looking at how many bits are spent per block at various parts of the frame. If you're willing to entropy decode your data, then we are no longer talking about compressed domain analysis in a strict sense. That may more appropriately be called transform domain analysis. However, many more opportunities open up. Transform domain analysis is much easier because the relationship between pixel and transform domain is usually tractable, or at least a lot more tractable than it is between the pixel domain and variable length domain. And what this means is that for a operation in a pixel domain, you can usually find an equivalent operation in the transform domain, and that's what makes the analysis easier. As a result, there are many papers on this topic, the earliest dating back to the 1970s. For example, here's a paper published at the Conference on Decision and Control in 1976, where the authors propose hierarchical search for image matching. In essence, they propose a multi-resolution transform of an input image where the low-resolution images are created from a high-resolution input image through low-pass filtering and downsampling, and they argue that because of that low-pass filtering, noise tends to be suppressed in the lower-resolution images, and that may give a more robust matching result if you're trying to search for a matching image within, say, a database of images. So transform domain image analysis is a very rich area of research. In fact, one could argue that the whole of traditional computer vision is a part of this area because most handcrafted features are a result of some kind of transform. For example, the very popular SIFT features are a result of the scale invariant feature transform. And because of that, the number of tasks that have been considered within this area is huge. And these include indexing, search, retrieval, classification, object detection, face detection, and so on. Most of the standard computer vision tasks. So I'd like to give a quick example of how HEVC bitstream syntax can be used to detect faces. So if we take a raw image and code it using BPG or HEVC intra and then entropy decode it, we can extract certain syntax information such as intra prediction modes, prediction unit size, and bin number per block. These are syntax features, and we can create a grayscale channel based on these features and then combine it into a color image, which is a feature image, just a visualization of these three features. And it turns out that you could train a neural network to detect faces in feature images like this. And the example is shown below. And the reason is that these bitstream syntax elements, especially say intra-prediction modes, contain information about the edges and edge directions. And so you could appreciate how that type of information is relevant to detecting faces or maybe other objects as well. At the same time, because transform coefficients aren't actually used in detection, you could scramble them. And so you could achieve a situation where a decoded image actually looks like this, where no obvious faces are visible, but faces can still be detected from these syntax elements. And so that type of system can achieve a certain level of privacy that a normal encoded bitstream cannot. Much like the image case, transform domain video analysis is also a very rich area of research for much the same reasons. The types of tasks that have been considered in transform domain video analysis are things like global motion estimation, object segmentation, motion segmentation, object tracking, action recognition, vehicle counting, and so on. The two examples here on the right show examples of object tracking from compressed video. And the tracking is actually performed based on motion vectors as well as some syntax elements from the H.264 bitstream. The yellow lines in each figure show the ground truth track of the centroid of the corresponding object. That would be the person in the left image and the little boat in the right image. And the blue lines show the estimated tracks based on motion vectors and syntax elements. And you can see that these tracks match fairly well, indicating that things like motion vectors can be quite useful in doing transform domain video tracking. So to summarize, we could say that there's been little work on the true compressed domain analysis, which in a strict sense means analysis of entropy-coded data. But there has been a lot of work on transform domain analysis, which is entropy-decoded data or data that hasn't been entropy-coded. And this, in a broad sense, includes traditional computer vision, because traditional handcrafted features are usually a product of some kind of transform, although those transforms are not necessarily the ones that are used in conventional codecs. But in parallel, there's been a lot of work on so-called compressed vision, which tries to mimic traditional computer vision, but using elements or features that are normally found in compressed bit streams, such as transform coefficients, prediction modes, motion vectors, and so on. I would also like to talk a little bit about applications that require multitask compression. One of these is traffic monitoring and management. So here we have a situation where cameras and other sensors are installed along the roads with the goal of helping to count vehicles, pedestrians, and so on, so that things like vehicle speed, traffic intensity, etc. could be estimated, or traffic violations or emergencies could be detected. Overall, the goal is to help manage traffic, avoid congestions, respond to emergencies quickly, and so on. The core tasks that need to be accomplished in this scenario are object detection and object tracking, from which all other analytics could be derived. And so a system that provides efficient compression for such an application should make sure that the least amount of bits are being used for these core tasks. It's also worth noting that human viewing may be needed occasionally, especially in case of emergencies or traffic violations, and so provisions should be made for such a task as well. Another related application is autonomous driving, where cameras and other sensors are mounted on the vehicle to help it understand and navigate its surroundings. Successful autonomous driving involves detecting vehicles, bikes, pedestrians, traffic lights, traffic signs, speed bumps, and so on. This involves a lot of sensory data and in turn requires high energy usage for processing such data. Some estimates say that about 2 kilowatt hours are needed for onboard processing in case of autonomous driving, and even more in cities where events of interest may occur more frequently. So one strategy to saving energy usage would be to offload some of this computation to an edge server where that's feasible. And this would involve communicating this sensory data, ideally in compressed form, to such an edge server. The core tasks in this case include object detection and tracking, object motion prediction, as well as human viewing occasionally in case of the need to review accidents and other events of interest. Besides traffic monitoring and autonomous driving, a large number of applications would fall under this umbrella of edge cloud collaborative intelligence. So this is a scenario that involves so-called smart sensors, and those would be sensors or edge devices that, besides capturing the signal itself, are also able to process this signal and perform some initial analysis of that signal and derive features from it. So those features would then be sent to the cloud where the remainder of the analysis is performed. The fact that features are sent over a communication channel means that compression is required here, but the benefits of this approach would be that privacy could be addressed by virtue of the fact that it's the features rather than the input signal that's being communicated, and the approach could also scale to the available resources at the edge device. A simpler device would implement simpler processing, and a more advanced device could implement a more sophisticated processing at the edge. The tasks that fit into this framework are almost any computer vision task, and human viewing, depending on the application, human viewing may also be required, and so this also calls for a multitask compression. There are a few existing coding standards related to multitask compression. One of them is MPEG CDVS, Compact Descriptors for Visual Search, which is specifically intended for image-related vision tasks such as search and retrieval, and considers coding handcrafted features such as SIFT and Fisher vectors. An extension of that effort was MPEG CDVA, Compact Descriptors for Video Analysis, which focused on video-related vision tasks, especially search and retrieval, and it also considered learned features besides handcrafted features. The current effort, called MPEG VCM, Video Coding Machines, could be considered a related but broader effort compared to CDVA, considering a broader spectrum of tasks and more mature learning technologies. So we've seen that despite seemingly a new research topic, there's actually quite a bit of history to multitask compression. Now, if we try to anticipate the future, it's important to realize that State-of-the-art performance on almost all vision tasks currently is achieved by deep neural networks. And even on the default compression task, which is input reconstruction, neural network-based coding currently provides state-of-the-art performance, at least for image compression, though not yet for video. In the list below, you'll see some of the prominent recent image end-to-end learning-based image coding methods which have come close or surpassed the best available traditional image codecs. So based on this scan of the present situation, it's easy to conclude that neural networks provide a really good unified framework for multitask compression, and that's going to be mostly the focus of this tutorial. So at this point we can take a short break for questions. So we saw that in the context of multitask compression, feature compression is very important. And in this part of the tutorial, we're going to focus on the theory behind feature compression. We're going to start off by reviewing some of the relevant concepts from information theory. The first of those concepts is entropy. So if x is a discrete random variable taking on values in some sample space, then the entropy of x in bits is defined as the sum over all possible outcomes of the probability of the outcome times log to the base 2 of the probability of the outcome, with a minus sign in front of the sum. So entropy is a measure of uncertainty or randomness within the random variable. And one of the basic results in information theory says that the entropy is the limit of lossless compressibility. In other words, if you were to encode the outcomes of the random variable into binary strings, then you need to spend at least h of x bits per outcome in order to have a code that can be completely and unambiguously decoded into the original outcomes. Examples of entropy, simple examples include a fair coin with heads and tails as possible outcomes, where the entropy is 1 bit per outcome, and a fair die with 6 sides, where the entropy would be close to 2.6 bits per outcome. Another fundamental concept is mutual information. So if x and y are discrete random variables whose joint probability mass function is p of xy, then the mutual information between x and y is defined as the sum over all possible pairs of outcomes of the joint probability of the outcome times log to the base 2 of the ratio between the joint probability of the outcome and the product of the marginal probabilities of the outcome. So mutual information is a measure of statistical dependence between random variables, and it's able to capture any dependence, whether linear or nonlinear. And its interpretation is that it is the amount of information in bits, if logarithm is to the base 2, that one random variable carries about the other. So simple examples include the case where the two random variables are independent, in which case their mutual information is 0. Or if you try to compute the mutual information between a random variable and itself, it reduces down to entropy. And that's kind of the information that a random variable carries about itself. And that's kind of intuitively very, very clear. Another important concept is that of a Markov chain. So a sequence of random variables, x to y to z, forms a Markov chain if this random variable z is conditionally independent of this random variable x given this intermediate random variable y. And if that's the case, then we'll have the following. The joint probability of x, y, and z can always be factored as follows. So p of x times p of y given x times p of z given y and x. That's always true. But if this chain happens to be a Markov chain, then you can drop this last conditioning on x, and so the joint probability factors out into P of x times P of y given x times P of z given y. So only one step conditioning is needed. And a simple example would be when z is a function of y, right? So when z is computed from y. In that case, regardless of what x is, x to y to z would form a Markov chain. And that's quite easy to see because z is simply computed from y. It's independent of x. And when y is given, there is no further dependence on x. And another important result that we're going to need is the data processing inequality. So what this inequality says is that if x to y to z forms a Markov chain, then the mutual information between x and y is no smaller than the mutual information between x and z. And so what this means is that a kind of a downstream variable further down in the chain has no more information about the first variable x than an upstream variable y. So the mutual information with respect to the input, if you will, x, cannot increase the further down the chain you go. And an extended version of the data processing inequality kind of considers 4 random variables in a chain, like x to y to z to w. And if this chain is a Markov chain, then the mutual information between these inner 2 random variables is no smaller than the mutual information between these outer 2 random variables. So again, it says that the closeness in the chain leads to higher mutual information compared to being further away in the chain. For most vision tasks, state-of-the-art features are learned features. For example, outputs of certain layers in a neural network. So let y sub I be the output of the ith layer in a feed-forward neural network. Using this notation, we can represent a neural network as follows. So the input is x, and then y1 is the output of the first layer, y2 is the output of the second layer, y3 is the output of the third layer, and so on, up to the final output of the network, which is the task variable t. It's important to note that x to y1 to y2 to y3 and so on forms a Markov chain. And this is simply because each layer output is a function of the previous layer's output. So that kind of trivially forms a Markov chain. And in fact, any chain from x to yi to yj would be Markov chain so long as I is smaller than j. In other words, j is further downstream compared to I. And that's true for any type of layer, regardless of the layer type, dense, convolutional, and so on. But many neural networks involve skip connections. So for example, if x is the input and then y1 is the first layer's output, we might have a skip connection from here to y3, where y1 is carried over and then concatenated or added to y3. What happens to Markovity in this case? Well, we can see that x to y1 to y2 to y3, right? So x to y1 to y2 to y3 is not a Markov chain. And that's because y3 is not independent of y1 when y2 is given, because y3 also depends on y1, right? And so we lose this conditional independence in such a case. So that's not a Markov chain. However, x to y1 to y3 to y4 and so on does still form a Markov chain, because conditioned on y1, y3 becomes independent of x. We don't need x anymore to compute y3. So we can conclude that Markovity still holds across skip connections, but not under them. So we are now ready to state and prove our first result related to feature compressibility. So we say that in a non-generative feed-forward neural network, in terms of lossless compression, intermediate features are at least as compressible as the network's input. So to show this, we're just going to show the sketch of the proof, and let Y be the set of intermediate layer outputs. So this could be one layer or could be a set of layers. And we decompose the mutual information between the input X and this set of features Y as follows. So this is entropy of Y minus the conditional entropy of Y given X. Now, the conditional entropy of Y given X is the uncertainty in Y when X is given. But because Y, the features, is a function of the input X, there is no remaining uncertainty left. So Y is known exactly when X is given. And so this conditional entropy is 0. And so we see that the mutual information between the input and the features is just the feature entropy. On the other hand, we can also note that this chain X to X to Y is a Markov chain. And this is a Markov chain because this first transformation is just simple identity function. And this second transformation is just the function of the network, so the features Y being computed from X. So this is trivially a Markov chain, and so we can apply the data processing inequality to it. So the data processing inequality says that the mutual information between X and X is no smaller than the mutual information between X and Y here. So on the one hand, the mutual information between X and itself is just the entropy of X, whereas the mutual information between X and Y, as we saw above, is the entropy of Y. So overall, we conclude that the entropy of Y of the features is no larger than the entropy of X, which is the input. And that's true not just for any one layer, but any collection of intermediate layers in the network. So this is great news. If intermediate features are more compressible than the input, then we can hope to do many of the computer vision tasks at a lower bitrate than what we would need if we were to just encode the input image or video. However, lossless compression is kind of very limiting. In practice, we usually want to use lossy compression to achieve much higher gains, and in practice, most image and video applications work quite well with lossy compression. So the question is, can we extend this result to lossy compression? In other words, can we claim that even in a lossy case, intermediate features in a neural network are at least as compressible as the input? And the answer is yes, but we're going to need some additional concepts from information theory. So in lossy compression, we will be quantizing data, and this quantization will incur certain distortion, and so we need appropriate concepts to capture these two notions. So if X is our data, or a random variable, and X hat is its quantized version, then the process of quantization is described by the conditional distribution of X hat given X. So a quantizer in this context is this conditional distribution of X hat given X. In practice, we often use kind of simple scalar quantization in a deterministic way, where when X is given, we know exactly which X hat, which representation level it's going to be assigned to. So for many practical quantizers, this conditional distribution is degenerate. It's basically an impulse located at the nearest representation level. But there are some quantizers with non-degenerate distributions that are actually used in practice. And an example is RDOQ, rate distortion optimized quantization, in HEVC and VVC. And in such cases, the representation level for a given X is not fixed in advance. So there is a certain probability distribution over the possible values of x hat given x. So a quantizer can be deterministic or probabilistic, but the theory can treat both of those cases through this conditional distribution. And so the other concept is distortion metric, so d of x hat comma x. And the purpose of distortion metric is to measure how much x differs from x hat. And the typical choices are things like L2 norm or mean square error or mean absolute error or something like this. But in general, distortion metric is chosen based on the application. So with the quantizer and the distortion metric defined, then we can define a set of feasible conditional distributions or feasible quantizers for a given distortion level. And this set is defined as the set of all conditional distributions such that the sum of the probability of x times the conditional probability of x hat given x times the distortion is less than or equal to d. So if we think about what this sum represents, p of x times p of x hat given x, that product is the joint probability of x and x hat. And so we see that this sum is essentially averaging across the joint distribution of x and x hat. It's averaging this distortion. So this is basically the expected distortion, right? And so the feasible set kind of says that it's a set of all quantizers that lead to expected distortion no larger than d. And within this expression, distortion is a function that's chosen for the application. P of x is the data distribution. It's not under our control, but the quantizer is under our control. So that's something that can be selected. And so once the set of feasible quantizers is defined, then the rate distortion function at the distortion level d is given by the minimum over all the feasible quantizers for that distortion level of the mutual information between x and x hat. Right? So it's the minimum of this mutual information across all the feasible quantizers for that distortion level d. And a fundamental result in rate distortion theory says that this is the minimum rate in bits at which you can encode the source x without incurring distortion greater than d. So just like entropy represents a fundamental bound on the lossless compression, r sub x of d, rate distortion function at d, represents the bound on compressing x at that distortion level. In order to use these concepts from rate distortion theory, in our case, we're going to have to make some adjustments. So let's have a look at the setup that we have. We have an input image or video, which is being mapped to some latent representation features y. This could be one or multiple layers in the neural network, which is then being mapped to the output. So we would like to compress x and compare that with the compression of y. But in both those cases, when we compress x or y, we don't really care as much about the distortion at x or distortion at y. What really matters is what happens at the output of the model. In other words, the effect of compression of x or compression of y on this output variable t. So we're going to redefine our feasible quantizers for x and y. We'll say that for a given distortion d at the output, the set of feasible quantizers for x is the set of these conditional distributions p of x hat given x, such that the expected distortion at the output is less than or equal to d. So this is f of x, right, that appears here in the expression for the distortion. And similarly, when we compress y, we'll say that for a given distortion level d at the output, the set of feasible quantizers, P of y hat given y, is the set of these conditional distributions that achieve the expected distortion at the output less than or equal to d. So we're using this mapping from features to the output here in the definition of this feasible set P sub y of d. So using these redefined feasible quantizers, we can now define the rate distortion functions for input and features relative to the distortion at the output. So we say that the rate distortion function for x at some output distortion level d is the minimum over all feasible quantizers of x for the output distortion d of the mutual information between x and x hat. And similarly, the rate distortion function for the features is the minimum over all feasible quantizers for y at the given output distortion level d of the mutual information between y and y hat. And again, it's worth stressing that in both cases we measure distortion at the output of the network, not at the point of compression. So that's one point at which this analysis deviates from the classical rate distortion theory, where you normally measure distortion at the point where compression is happening. Now, in terms of this output distortion, this distortion metric could be any metric that is appropriate for the network's task. For example, regression networks might use mean square error, classification networks might use cross entropy or classification accuracy or something like that. It turns out that it actually doesn't matter. We won't be using an explicit equation for the distortion metric. What really the only thing that matters is that the same distortion appears in the definition of the feasible quantizers for features and the input. So we are now ready to state and prove the following claim. In a non-generative feed-forward network, in terms of lossy compression, intermediate features are at least as compressible as the network's input. And the way we formally state that is to say that the rate distortion function at y is always below or at the most equal to the rate distortion function at x, where we keep in mind that distortion is measured at the network's output, whereas the rate or the bits are measured at y and x respectively. So we're going to give a brief sketch of the proof. We're omitting some details, but hopefully the main ideas will be conveyed. So we start by saying let d, the output distortion level, be given, and let p star be the optimal quantizer for input compression. In other words, it's the quantizer that achieves the rate distortion function for that given d at the input. This optimal quantizer may or may not be unique. If it's not unique, any one of the optimal quantizers would do. So once we pick P star, then we perform the following thought experiment. We draw inputs according to the input distribution P of x, and for each input x, we process it in two ways. First, we map the input x through that portion of the network that maps input to the features. So that's what we call G. So x creates y, right? And the other way in which we process the data is we quantize it first using the optimal quantizer P star to obtain x hat, and then pass x hat through that same portion of the network to create the other set of features y tilde. So y and y tilde are different because they're produced by different inputs to the network. One is uncompressed, the other one is compressed. Either way, we see that any given data point x produces two sets of features, y and y tilde. So by pairing up y and y tilde, we can basically create this conditional distribution of y tilde given y. And that is effectively an induced quantizer at this point where the features are, right? That quantizer is induced by the optimal quantizer for the input. Next, we showed that the induced quantizer, Q of y tilde given y, satisfies the distortion constraint for distortion level D. And that's easy to see because the induced quantizer, Q, is just an intermediate processing step in the network for the optimal quantizer P star, which was applied to the input. So if P star has satisfied the distortion constraint, then this induced quantizer, just being an intermediate step in the network, surely satisfies the same distortion constraint. In fact, it achieves exactly the same distortion because it's just an intermediate processing step. So this basically shows that Q of y tilde given y is one of the feasible quantizers for the features at that output distortion level D. So that's the first point to note. The second point is to apply the data processing inequality to the following Markov chain: y tilde to x hat to x to y. So this looks a little bit strange, but remember that on the previous slide we actually had a Markov chain x to x hat to y tilde. So starting with uncompressed data, compressing it using the optimal quantizer, and then pushing that through the network to obtain these features y tilde. So x to x hat to y tilde was a Markov chain, and then we recall this basic result that Markov chain is also Markov in reverse. So for that reason, y tilde to x hat to x is also a Markov chain, and then we just stick one more processing step to it, and this is that initial portion of the network that maps the input to the features. So that was function g here. So overall, this is a Markov chain, y tilde to x hat to x to y, and therefore we can apply that extended version of the data processing inequality to conclude that the mutual information between y tilde and y, which is here, is no larger than the mutual information between x hat and x, which is here. Okay, and that's true for any kind of quantizer of x. But because we are using the optimal quantizer for x, we're using P star, then this mutual information, x to x hat, is in fact the rate distortion function at the input for the distortion level D. So this mutual information is in fact R sub x of D. So at this point we've concluded that the mutual information between y and y tilde is no larger than the rate distortion function for x at this distortion level D. So overall, what this means is that this induced quantizer is, number one, feasible for the distortion level, right? And number two, achieves a rate that's no larger than the input compression, best input compression rate at this distortion level D. Right? So if that particular induced quantizer achieves a rate that's no worse than the rate at x, the best one, which would be the minimum over all feasible quantizers, surely can't be worse than that. So that's why R sub y of D, the rate distortion function at the features for that distortion level, is no worse than this mutual information here, which, as we see, is at least as good as the rate distortion at the input. So overall, this shows that the rate distortion at the features is no worse than the rate distortion at the input, and that's what completes the proof. So using these basic results, we can now make other claims. For example, in a non-generative feed-forward network, deeper layers are more compressible, whether in terms of lossy or lossless compression. So explicitly, we could say that the entropy of a deeper layer is no higher than the entropy of a shallower layer, and the rate distortion at a deeper layer is no worse than the rate distortion at a shallower layer, again when distortion is measured at the network's output. And these are quite easy to prove. Essentially, you would use the same steps as before, just with replacing the input x with yj and features y with yi. So let's summarize what we've talked about so far. Theory shows that intermediate features in a non-generative neural network are at least as compressible as the network's input, both in terms of lossy and lossless compression. That's true for any non-generative network. In other words, any network that doesn't introduce new randomness inside the network by sampling from some random distributions. And that includes many of the popular state-of-the-art computer vision networks and other networks. And this is true regardless of what the task is. Remember, we didn't assume anything about what this T is. So task can be anything. And in fact, there could be more than one tasks, right? So T, you can imagine that the output T is some composite tensor that includes object bounding boxes, class labels, segmentation masks, pose orientations, or anything. So this is also true in multitask models. However, theory only talks about the limits. In other words, it kind of assumes that you're using ideal codecs, right? It talks about the limits, what the best that's possible. Practical codecs may be quite far from those limits. Also, theory shows what's possible, but not really how to get there. And so there is still a lot of work to be done on actually trying to approach those limits. So to me, that seems like an ideal situation for grant proposals. Nonetheless, we still have to ask at this point, what can we expect from practical codecs that exist today? In other words, can we see any of this predicted behavior using codecs that are not optimal? So let's look at a simple toy example of feature compressibility on a simple network and with a practical codec. So we're going to focus on this simple convolutional network with 7 layers. So there's 5 convolutional layers and then 2 fully connected layers at the output. And the network is trained on cats versus dogs classification. So the input is an image and the network is trying to predict whether the image shows a cat or a dog. And it was trained on a Kaggle's cats versus dog dataset. So it's certainly not a state-of-the-art network for this problem. I think its accuracy when trained is around 92%. State-of-the-art models for this problem basically solve it, the accuracy higher than 99%. But the goal is simply to compare input compression versus feature compression in terms of the resulting classification accuracy. So input images will be compressed using JPEG. So what we show here at the top are 4 different decoded images, each one of them compressed and then decoded using JPEG. And the one in the top left is the lowest quality, that's the lowest bitrate or lowest file size, and the rating increases as we move to the right. What we are showing below is a visualization of the features from the various layers of that convolutional network. So here, these are layer 1 features, below them layer 2 features, and so on down to layer 5. So the features have been visualized by essentially taking a few feature tensor channels from that feature tensor at a particular layer, and then tiling them up and showing them as a grayscale image. So you can kind of see roughly the resolution of each feature channel in these layers, and it kind of goes down as we go deeper in the network. So now these tiled up feature tensors represented as a grayscale image, those will also be compressed using JPEG. So we use JPEG both for input compression and feature compression. And here on the right is a compression versus accuracy, or in other words, accuracy versus rate curve shown for compressing various points. So the solid green line represents input compression. That's the one shown here. And then we have 5 other curves showing the rate accuracy for compressing a particular layer. So what we see here is that input compression in terms of rate accuracy seems to be about as good as compressing layer 2, and in fact better than compressing layer 1. Because for a given accuracy, we can achieve a lower file size or lower rate by compressing input. That seems not to agree exactly with the theory. Remember, theory predicted that each layer is more compressible than the input. So why is that? And the answer is quite simple. We are using a suboptimal codec, right? Remember that theory talks about the limits, in other words, kind of assumes using optimal codecs. We know that JPEG is suboptimal even for input images for which it was intended, and it's certainly a lot more suboptimal for encoding intermediate features like this. So it's the fact that we're using a suboptimal codec that we don't see exactly the behavior that the theory predicts. However, we still do see quite a bit of that behavior if we look, kind of consider the trends here. So for example, we do see that layer 2 is more compressible than layer 1, and layer 3 more than 2, and so on. So we do see this trend. And in fact, features do become more compressible than the input if you go deep enough. So starting with layer 3, we do get better rate accuracy than compressing the input. So some trends, some behaviors predicted by the theory can already be observed with practical suboptimal codecs. So here's another example of feature compressibility, this time using a more sophisticated network, YOLO version 2 object detector, and a more sophisticated codec, BPG in this case. And this codec is used to compress both the input and the tiled features in this case. So in the experiment, YOLO version 2 was split at 2 different points, max pooling layer 11 and max pooling layer 17, and the same kind of experiment as mentioned previously was conducted, measuring the file size versus mean average precision, which is the usual accuracy metric for object detection. And so we see that simply compressing these intermediate features of the network gives gains of up to 60% compared to compressing the input. Those are on this rate accuracy graphs. Those are the solid blue curve for the max 11 layer and the solid red curve for the max 17 layer, whereas input compression is represented by the solid green curve. Now, if you're willing to retrain your model, taking into account this feature compression, then model becomes more robust towards feature compression, and in fact you can achieve even higher gains here, so up to 70% rate gain compared to input compression using BPG. So based on the results presented so far, it would seem that you have to move the compression point further downstream, deeper into the model, in order to achieve compression gains in terms of rate distortion. That, of course, would make encoding more complicated because you have to process more layers prior to encoding. However, there is another way to achieve compression gains, and that's through distillation. So in this context, what distillation means is compressing a certain layer in a model, but with the goal being to match accurately another layer deeper into the network, right? So not moving compression point from, let's say, layer Y1 to Y3, but compressing layer Y1 in order to kind of minimize distortion of layer 3 features. This is what we mean by distillation in this context. And there is a proof that under certain conditions, compressing to match or distill a deeper layer is better in the rate distortion sense. So far we talked about feature compression in very general terms, without really worrying about whether the network's output is one task or multiple tasks. Next, we're going to focus a bit more on the case of coding for multiple tasks. The first thing to note is that different tasks have different distortion metrics, and these distortion metrics may be on different scales. For example, some metrics are on a scale 0 to 1, like SSIM, for example, and others might be on a much larger scale, like PSNR. So when we consider the relative importance of different tasks, we have to somehow take into account that different distortion metrics are on different scales. Of course, ultimately, the goal in compression would be to allocate bits appropriately to satisfy all tasks. So one way to bring task distortions to a common scale would be to define task distortion as follows. So for the ith task, the distortion could be defined as the relative change in task accuracy due to compression. So in this expression, A bar is the task accuracy without compression, and A sub I is the task accuracy after compression. So D sub I in this expression would be the relative change in task accuracy due to compression, and it can be expressed on a scale 0 to 1 or in terms of percentages if you multiply it by 100. And this allows us to bring multiple task accuracies such as MAP, intersection over union, Jacquard index, PSNR, SSIM. All of those could be brought to the same scale using this transformation. For our analysis, it'll also be useful to define a tractable rate distortion model that relates the distortion of different tasks, or even the total distortion across tasks, as a function of the rates of coding units whose bits are we trying to optimize. So, for example, one such useful model would be like this. So here DI is the distortion of the ith task, and it's a function of n rates, where these rates are the rates for the corresponding coding units. These could be different features in a network or different feature channels in a tensor of a network. And we can express that as the following sum here. So it's a sum over all the rates of a certain exponentially decaying function of a rate plus some offset. So why this particular model? Why this would be a good model to model our distortions? So it has multiple benefits. The first is that it makes sense considering other results in rate distortion theory. So in the few cases where the rate distortion function for a source is known explicitly, and those would be things like Gaussian source with the mean square error distortion, or Laplacian source with the mean absolute error distortion. In all those cases, the distortion decays exponentially with the rate, and so this kind of model acknowledges that. So from that point of view, the model makes sense. Almost as importantly, it fits the data rather well. So on the graph here on the right, we see an example where the green surface is the rate distortion surface of a total distortion of two tasks as a function of two different rates here. And so the green surface corresponds to measured distortion at the given rates, whereas the gray surface is the fitted surface, and the fit is quite good. In most of our tests, we obtained the R-square coefficient of 0.94 or higher, which indicates a pretty decent fit between the measured surface and the fitted surface. And the third benefit of this model is that it's tractable. Because it is convex and monotonically decreasing, we will be able to say more about the solutions to the bit allocation problem than we would if we didn't have these properties. So using that distortion model, we can now state the following claim. If Wi represents the relative importance of task I, such that all these Wi's are non-negative and they add up to 1, and if the total distortion across tasks is the weighted distortion of each task, which is also represented using that exponentially decaying model, then the optimal bit allocation to minimize the total distortion subject to a rate constraint is given by this expression here, which is a function of these parameters of the rate distortion model and the Lagrange multiplier lambda. And this notation, square bracket with a plus, indicates the non-negative portion of x. So this type of result is sometimes referred to as inverse water filling, and it can be derived using Karush-Kuhn-Tucker conditions. And so the key component here is that the kind of cost function is convex and the constraint is also convex, and that's what allows us to use KKT conditions to derive this result. So that's nice. In this case, when relative task importances are given and the total distortion is that weighted combination of task distortions, we can have an explicit equation for the rates allocated to these different coding units. But what if relative task importances aren't known in advance? What if we don't have those Wi's in advance? Can we still say something about optimal solutions to the bit allocation problem? So really, the general multitask bit allocation problem is a problem like this. We want to simultaneously minimize all the task distortions rather than their linear combination. So all task distortions need to be minimized subject to the rate constraint. So this leads us to the notion of Pareto optimality, which is the optimality notion appropriate for multi-objective tasks. And it can be solved numerically. There are a number of numerical solvers for problems like this. But in our case, because of the particular rate distortion model, we can actually solve it analytically, at least in some cases. And in particular, analytic solution to the problem can be given in the case when there are two coding units and any number of tasks. So we are focusing on the case of two coding units and any number of tasks. And in this case, we can make and prove the following claim. If R1, R2 superscript I is the solution to the bit allocation problem for the ith task, and if we look at the extremes of those bit allocation solutions across all the tasks, then we can show that any point on the rate constraint line, R1 plus R2 equals RT, between those extremes is a Pareto optimal solution, and there are no Pareto optimal solutions outside of that line segment. So we're not going to go through the details of the proof, but just to illustrate what this actually means, we can look at the graph here below. And first note that optimal solutions must be on this line, which is R1 plus R2 equals to RT. Even though the constraint is less than or equal to RT, optimal solutions must be on this line with equality. Because if you've spent fewer than RT bits, you can simply take the leftover bits and allocate it to any coding unit. And because of the monotonically decreasing distortion surfaces, that would actually improve the distortion. So optimal solutions must be on this line. So if we now focus on this line and basically look at the plane that intersects all the distortion, task distortion surfaces above this line, we'll find that some tasks may have a distortion like this as a function of the rates on this line. So blue line represents the distortion of one of the tasks, and its optimum is at some point. Yellow curve represents the distortion of some other task, and its optimum, its lowest value, is at some other point, and so on. So what the claim says is that you find all those points that optimize each task individually, and then you look at the extreme points, the kind of leftmost and the rightmost point among all of those. And it turns out that any point on the line in between those two extremes is a Pareto optimal point, and no point outside of that line segment is Pareto optimal. So we're able to make and prove this claim because of the specific shape of rate distortion surfaces, the convexity and the monotonicity. But it's nice that at least that shape, which kind of makes sense from a theoretical point of view, allows us to say something like this about bit allocation for multitask coding. So let's look at a practical illustration of the previous result. Here we will focus on the following multitask model that's been trained on the Cityscapes dataset. So what the model is trying to do is to predict semantic segmentation and depth estimation from an input image. And we also added a third task of input reconstruction. That'll be useful later, but in this particular example, we'll just focus on these two tasks of semantic segmentation and depth estimation. So the model is split at a particular point where two feature tensors need to be encoded, and those are the coding units to which we will be allocating bits, and both are being encoded using JPEG 2000 so that we can control the rate fairly precisely. So what's shown here in the bottom left plot is are the operating points in the distortion plane. So we're showing distortion of task 1, which would be semantic segmentation, and normally segmentation distortion is something like intersection over union, but remember that we've mapped them to that common kind of percent reduction type of distortion. So that's D1, corresponds to distortion of semantic segmentation, and D2 is the distortion for disparity estimation. So each of the gray points here is a point on the distortion plane that can be achieved by some allocation of bits between these two feature tensors, these two coding units. So the red points here are kind of the extremes of the feasible region. So they kind of correspond to using up all the bits that are available within the total rate constraint. However, rate points, distortion points that are shown in red here are not Pareto optimal. And the reason why they're not is that if you are located at one of these points, you can see that you can change your bit allocation a bit to move this way, and that type of move would improve both distortions simultaneously. Whereas the requirement for Pareto optimality is that you cannot improve one objective without hurting another. So in fact, Pareto front for this problem is shown by these green points here. So these are the points at which it is true that improving one distortion has to hurt the other. And so we can see that these distortions are somehow the closest that this feasible region gets to the ideal point, which would be the origin, zero distortion on both tasks. In some sense, these are the closest points to that ideal position. And so the previous result basically predicts where these extremes of the kind of Pareto front will be, and kind of shows that this will be the Pareto front. The green points that are actually shown here are the solutions obtained from numerical Pareto solvers, and so they can get you discrete solutions here, and you see that they fall on that front. But the previous result kind of characterizes the whole front. And the curve, the plot on the right here, shows the actual Pareto set. So those are the rates that achieve the Pareto front. And again, the previous result kind of says that every point between these two extremes, in our case we just had two tasks, so we get 2 points on that rate constraint line, and the result said that everything in between is a Pareto optimal solution and nothing outside of it is. And you can see that the numerical solvers have kind of sampled this Pareto front, but the result gives you confidence that in fact every point here is Pareto optimal. So if you were building a system like this and you wanted to have it operate optimally without knowing in advance, you know, how important would be segmentation versus depth estimation and so on, from this type of analysis you could tell that, okay, well, we're going to need at least whatever 540 kilobits for rate 1 and at least whatever 380 kilobits for rate 2 in order to have the system operate optimally. So those are kind of useful results for system design. So this concludes the theory portion of the tutorial, and we can now make a little pause to see if there are any questions. So in the next part of the tutorial, we are going to look at the current practice, or perhaps more appropriately, the current research on the topic of multitask image and video compression. Most of the multitask compression systems that we're going to look at will include input reconstruction as the default task, and then one more computer vision task. And in some cases, we will have more than one computer vision task. So let's look at this situation. The input image is mapped into a latent representation which will be compressed, and from which we will then be able to reconstruct the input image as well as perform some computer vision task. In the discussion so far, we didn't really worry too much about which parts of this latent representation support which task. In fact, it seems as if the entire latent space supports all the tasks. But we'll see that a better design is possible. And the first thing to note is that if this input image is reconstructed sufficiently well, then we can perform the computer vision task based on this reconstructed image. In fact, this is very common in practice. Computer vision is built up on reconstructed images rather than raw images. So, for example, image classification models are trained and tested on JPEG images, not raw images. So this is quite common in practice. Now that we know this, we can apply the data processing inequality to this Markov chain from y to x hat to t. And from here we can conclude that the mutual information between y and x hat is larger than the mutual information between y and t. In other words, what this says is that the latent representation carries more information about x hat than it does about t. So based on this conclusion, we can then arrive at the following structure for the latent representation. So this y, which will normally be a feature tensor, will be split into two parts. And one part of it will be dedicated to this computer vision task T, whereas the whole of the latent representation will be dedicated to the default task of input reconstruction. So this way we kind of respect this information inequality, saying that the latent representation carries less information about the computer vision task than it does about input reconstruction. And we refer to this structuring of the latent space as latent space scalability, because if we only need to execute the computer vision task, we only need to decode this part of the latent space. We don't have to touch this enhancement layer. This will only be needed if we want to fully reconstruct the input image. So let's look at one example of a specific two-task system developed based on this concept of latent space scalability. So here we have this system shown in green is an end-to-end neural image codec, and in this example this is basically the Chang 2020 end-to-end neural image codec, but it has been redeveloped and retrained to support this latent space scalability. So the input image is subject to the analysis transform and then encoding into a latent representation Y here, which consists of a number of feature channels. And when the full latent space is decoded, the input image is reconstructed as x hat. But a part of this latent space is then dedicated to the computer vision task, and the computer vision task in this particular case is object detection. And to accomplish that task, we use the backend of a YOLO version 3 model, and specifically the backend here means the whole model starting with layer 13 and then all the way to the end, producing the output. And because the latent representation here is not exactly the latent representation that the backend expects, we also have to insert a latent space transformation here, which is just another kind of neural network, if you will, that maps one latent representation into another. And so we call it a latent space transform. So when only the computer vision task is needed, we only decode a portion of the latent space of this codec, transform it through the latent space transform, feed it into the backend of the YOLO version 3 model to obtain object detection results. And when the full input image needs to be reconstructed, then we simply decode the entire latent space. So the system can be trained end-to-end to accomplish these two tasks. But in the training, we kept this backend frozen so that essentially only latent space transform and the encoder and decoder are being trained to accomplish these two tasks. The loss function looks like just a standard rate distortion loss function. So there is a rate estimate R plus lambda times total distortion. The rate estimate is obtained using conventional methods that are now pretty common in trainable image coding. And the distortion here is composed of two distortions. So one is related to the input reconstruction, and that's the MSE here at the reconstruction output. And the other one is the feature reconstruction distortion. So that's measured here at this input to the CV backend. And so the system will try to reconstruct these features that the backend expects as accurately as possible by minimizing this distortion here. So this kind of shows you that you can, in principle, train this system in a so-called self-supervised way. You don't really need labels here. If you use a pre-trained backend, you can essentially accomplish this training just by feature matching at this point. So during training, obviously, gradients of this loss function are computed and they update the parameters of the model. Now, the gradients of this term, the feature matching term, only flow into this portion of the latent space over here. So only flow to the portion that's dedicated to object detection. And so that's what serves to sort of concentrate and pull the information relevant to object detection into only one part of the latent space. Whereas gradients from this term, which is the distortion related to input reconstruction, flow into the entire latent space, and so that information gets distributed through the whole latent space. So let's look at some results on the COCO dataset. So this graph shows the bit rate versus mean average precision for various cases. The black dashed line here at the top is the system performance without compression. So that, in other words, that's just the performance of YOLO version 3 fed with input images without any compression. And the two dashed lines below it show the 1% and 2% MAP drop. So the group of lines here that show MAP versus bitrate correspond to various codecs applied to input images. So the green line is HEVC, the light blue line is VVC, and then we have the two prominent end-to-end trainable image codecs. And this red line here is the performance of this system that we've just described, but when only decoding the portion of the latent space dedicated to object detection. In other words, only that kind of base layer. And if you measure BD rate performance between this red curve and the others, what you'll see is that you're getting 40 to 50% gains in the bit rate, which translate into about 2.5 to 4.5% improvements in MAP at the equivalent bit rate. So, just like theory predicted, information related to a computer vision task takes fewer bits for the same performance than it would take to encode the input and then use the decoded version of that input to accomplish the same task. So now let's look at the case of three tasks, namely input reconstruction, instance segmentation, and object detection. Looking at these three tasks, we note that basically from an input image, we produce a latent representation Y from which input image can be decoded. And then once we have a reconstructed input image, we can then run a segmentation model to obtain segmentation masks. And from those, you can obtain detection results just by putting bounding boxes around segmentation masks. So looking at this Markov chain from Y to X hat to T2 to T1, we conclude that the latent representation Y carries more information about the input reconstructed image X hat than it does about segmentation masks, and in turn this information is larger than the information it carries about detection results. So using this conclusion, we can now structure the latent space according to this concept of latent space scalability again to support these three tasks efficiently. So here's the system design based on that conclusion. Again, we start with an end-to-end neural image codec whose latent space supports input reconstruction. A portion of that latent space is then dedicated for instance segmentation, and a further subset of that is dedicated for object detection. And here we use Detectron as the backbone for these two tasks, and in particular object detection here is carried out using faster RCNN, whereas instance segmentation is carried out using mask RCNN. So here are the results again on the COCO dataset. The top figure here shows bits per pixel versus MAP for object detection, and the bottom figure shows bits per pixel versus MAP for instance segmentation. In the top graph, we only need to decode the lowest layer, the base layer in our case. And then we compare that against the other conventional image codecs, HEVC, VVC, and the two prominent end-to-end trainable image codecs. And you can see that the bitrate versus MAP curve is quite a bit better than input compression. And the same is true for instance segmentation. In this case, we encode the base layer and the first enhancement layer to accomplish the segmentation task. But again, that costs, for a given accuracy, costs far fewer bits than it would if we were to encode input and then perform the same task from the decoded output. In terms of the BD bit rates, the savings are up to almost 80% compared to conventional image codecs in terms of BD bit rate, and that translates into something like 2.3 up to almost 4 percentage points on the MAP scale. That's for object detection, and the similar gains are observed in the case of instance segmentation. Of course, we also have to test the system performance on the input reconstruction task, and that's done here in these two graphs on the Kodak dataset. So this top left graph shows the performance of bits per pixel versus PSNR for a number of codecs here. So this lowest line here is the JPEG codec. That's a bit of an outlier. Comparatively, the other codecs are somewhat similar. So we have again HEVC, VVC, the two prominent trainable image codecs, and then our 2-layer and 3-layer system. So the 3-layer system performs about the same as HEVC. So that's this red line here with the circles. Whereas the 2-layer system performs better, and it's closer to the performance of VVC and the two other trainable image codecs. If you want to get more precise measurements in terms of the BD bitrate, you can see here when the BD bitrate is measured on this graph, so against PSNR, there are gains obviously against JPEG and HEVC, and even this trainable end-to-end image codec of Minen and others, but there's loss against Chang 2020 and VVC. This graph here on the right shows the performance in terms of bits per pixel versus SSIM. And here, in fact, we see that our 2-layer system seems to be about the best here, kind of near the top of the curve, whereas the 3-layer system is, again, a little bit worse, but not as bad as it was in case of PSNR. And that's quite well known by now that these trainable codecs perform quite well in terms of metrics like SSIM. So in terms of the BD bitrate results, you can actually see that this two-layer codec that does object detection in the base layer and then input reconstruction in the enhancement layer is in fact achieving gains against all the other codecs in this comparison. But the three-layer one isn't. However, it is still obviously better than the old JPEG as well as HEVC, and kind of comes close to VVC and the codec of Minen and others. We also notice that there is a degradation in performance of going from 2 layers to 3 layers. So adding one scalability layer seems to degrade the performance of the system. And that's kind of in line with the earlier work on scalable video coding, where people have compared how much does it cost in terms of bitrate performance to add a layer of scalability. And those numbers in the literature suggest that between 10 and 30% gets added to the bitrate when you add one scalability layer. So these results are kind of in line with those earlier studies on scalable video coding. So let's look at a few other examples of multitask image coding systems from the recent literature. So this system shown here at the top is intended for scalable face image coding, and the base task here is face recognition. So the base layer bitstream here is derived from like a sketch of an image and includes the information about the key points, facial key points, landmarks in an image. So given those key points, the generative decoder will be able to synthesize a face according to those facial landmarks, and that'll be used for face recognition. Meanwhile, the enhancement bitstream contains information about color and texture, which should help the decoder create a more faithful reconstruction of the input image. Another example from the recent literature is this semantic to signal scalable coding, where it's assumed that there is a kind of like a deep backbone that accomplishes a certain task, and the example mostly treated in that paper is image classification. So you can think of this being a backbone for image classification, and then the base layer is the deepest feature coded within that backbone, and the enhancement layers are the information that's needed to recover one layer up from the previous layer. So there's a series of enhancement layers that help the decoder recover features upstream, and then with the final layer you can then recover an approximation to the input image. So while most multitask coding systems use trainable codecs, here is an example of a system that's based on traditional codecs. So the goal here is to enable various tasks derived from segmentation maps, and so we can think of this system as essentially having a base layer that encodes segmentation information. So that's coded losslessly using FLIF. Then the next enhancement also losslessly codes a bit of information that's needed to produce a reasonable preview of the input image. So that will be like the first enhancement, and then finally the second enhancement is a bitstream coded using VVC, which then basically provides the residual necessary to recover a good approximation to the input image. So here's another example of a multitask human-machine image coding system where the base layer provides information for a computer vision task, which is classification in this case, as well as a preview of the input image. And then the enhancement layer provides additional information necessary to reconstruct a high-quality version of the input image. And there are a few other methods in the literature that consider coding for a computer vision task that also allow for a preview or another task related to human vision. So let us now look at another multitask system where both tasks are kind of related to human viewing. This is compressed domain denoising, and this was in fact one of the scenarios in the JPEG AI call for proposals. So here the goal is to take an input noisy image X, encode it into a latent representation Y, from which both the reconstructed noisy image X hat can be recovered, but also the denoised image X bar can be recovered. So the same latent representation is supposed to facilitate the recovery of a noisy image as well as a denoised image. So there's no obvious machine vision task here, but nonetheless we can analyze this situation using the same tools we've developed so far. So first, we note that if we have a reconstructed noisy image, we can apply denoising to it to create a denoised image X bar. And then we apply the data processing inequality to the Markov chain Y to X hat to X bar. So we have Y to X hat to X bar being a Markov chain, and the data processing inequality says that the information about the noisy image contained in the latent space is greater than or equal to the information about the denoised image. And so what this means is that we should be able to structure our latent space in such a way that the full latent space allows reconstruction of the noisy image, but only a subset of that latent space is dedicated to the denoised image. So just like before, we can start with end-to-end trainable image codec and restructure its latent space so that a portion of it is dedicated to the information about a denoised image, whereas the whole of it is used to reconstruct the noisy input image. So in some sense, this latent representation will separate the denoised signal from the noise information. So here are some of the experimental results. So for this scalable denoising system, we again started with the Chang 2020 backbone and restructured its latent space into a portion dedicated to a denoised image and then the portion dedicated to noise. The resulting system is called the Joint Image Compression and Denoising JICD. So it was trained on the CLIC dataset with 3 levels of Gaussian noise with standard deviation 15, 25, and 50. What's shown here are the results for the strongest of these, so the noise standard deviation of 50. The systems compared against CBM 3D, which is the sort of gold standard handcrafted denoiser for color images, and FFDNet Clip, which is a state-of-the-art trained model for clipped noise. The results are shown here. So the kind of a purple line at the top is the denoising performance of FFDNet Clip. The dashed line green is the performance of CBM 3D. The blue line is the approach where you first encode the noisy image using the default Chang 2020 backbone and then denoise the decoded image using FFDNet Clip. So it's kind of a combination of state-of-the-art models for compression and denoising, but a kind of combination in series. Whereas these two curves here correspond to this joint image compression and denoising approach. And the one of these curves is the system trained explicitly for the noise level at which it is tested. The other one is trained for variable sigma. So in other words, during training, you sample the noise from all these three categories, and they work about the same. And what's interesting here, at least for this high noise level, you'll see that even with compression, these systems are able to provide better denoising than CBM3D without compression. However, this noise level of sigma 50 is quite high, unlikely to be found in practice, but found very frequently in the literature. So if you want to compare with the work in the literature, you're kind of forced to work with some of these unrealistic noise levels. So what we also did is compare the performance on a more realistic noise, kind of at the lower noise level and unseen during training. So these results here correspond to this Poissonian Gaussian noise model, whose parameters have been fitted on the smartphone image denoising dataset, which is a collection of smartphone images with somewhat more realistic noise. And the same sort of noise type was used in JPEG AI exploration experiments. So you can see here in the results that all systems do better now. The PSNRs are higher. Nonetheless, this joint image compression and denoising approach is still able to provide better denoising performance than CBM3D at a sufficiently high bitrate while doing compression. And of course, the FFDNet clip still remains the best denoiser per se, but it doesn't perform compression. So here are some visual examples. Here at the bottom is the noisy image and the clean image prior to adding noise. It's hard to tell the difference when you look at the full image. So up here, zoomed in version of one of the regions of the image is shown, and you can see that there's a little bit of that noise here once you zoom in enough. This result is produced by first encoding the noisy image using Chang 2020 model and then denoising the decoded image with FFDNet clip. And this is the result produced by this joint image compression and denoising method. And you can see that this joint method tends to produce fewer artifacts near the edges in some of the regions, as well as seems to be better in producing colors. So this white region here inside the circle seems to be a little bit pinkish with this approach, but it gets back closer to the original white with the joint denoising approach. So let's look at the other task now, which is the reconstruction of the noisy input image. In this case, in the joint compression and denoising approach, we use the whole latent space, not just the base layer, but the whole latent space to recover the noisy input. And the approach is being compared against the Chang 2020 backbone on which it is based. So as you might expect, the performance is fairly similar across different data sets. There's a slight BD bitrate loss on one of the data sets that includes the low resolution images and some gain on the three other data sets. But overall, the performance is quite close to the default Chang 2020 backbone. And here are some results on the quality of reconstruction of noise distribution. These are obtained on one of the images from the JPEG AI test set, and they represent the case of Gaussian noise with sigma 50. So in each of these 6 figures, we see 2 histograms. The green histogram is the distribution of the noise in the input noisy image, and the red histogram is the distribution of the noise in the reconstructed noisy image. And the 6 figures represent encodings at different bit rates. So starting with the lowest bit rate and going to the highest bit rate. So we see that at low bit rates, there's only so many bits to spare, and not many bits end up allocated to the noise. So only a very narrow noise histogram with a relatively small variance can be supported. As the bit rate goes higher, we can support higher and higher noise variance, and at higher bit rates, the distribution of the reconstructed noise starts matching the distribution of the input noise reasonably well. So to summarize, there are already a number of papers in the literature that describe various multitask image compression systems. In most of those cases, the base task is the computer vision task, usually classification, sometimes object detection or segmentation. And besides the base task, there's usually additional task which may be related to computer or human vision. What has been convincingly demonstrated so far is that computer vision tasks require fewer bits than input reconstruction. So that's been practically demonstrated in all of these cases, all these papers that describe multitask compression systems, and there is also a theoretical justification for it. So I would say that that is a major milestone in our understanding of multitask compression. In the old days of compressed domain analysis in the bit streams of conventional codecs, people were very shy about claiming that bits could be saved for the purpose of computer vision. And the reason is that in a conventional bit stream, sometimes you're forced to entropy decode certain syntax elements that you wouldn't use in your analysis. So there is no obvious bit savings. But we now have enough evidence to claim that this indeed is possible. So that's an exciting breakthrough. However, there's still a ways to go. Just to give a quick example, if you consider the task of ImageNet image classification with 1,000 classes, each image contains about 10 bits of information relevant to that task. And that works out to be about 2 times 10 to the minus 4 bits per pixel for a 224 by 224 image, and even less if you consider larger image resolution. However, the best currently available feature coding methods require more than 0.01 bit per pixels to maintain accuracy. So you'll see that there is 2 orders of magnitude of gap between the theoretically best performance and what we currently have, meaning that there is still a lot of room for improvement. So next we're going to switch to multitask video compression, and there's far less work on that topic for now, but there are a few papers and we're going to describe them briefly. So here's an example of a system for 2-task video compression built upon this concept of latent space scalability. The base layer is dedicated to object detection, and the enhancement layer supports input reconstruction for human viewing. What's shown here in the top right is the GOP structure of this codec. Intraframes are coded in a task scalable manner using this notion of latent space scalability, and the encoder is shown here and essentially is the same one that we presented before for image coding. Intraframe is being encoded into a structured latent space where the base layer can support object detection backend through a latent space transformation, whereas the full latent space supports input frame reconstruction. So machine vision, in this case object detection, operates at a reduced frame rate when only the base layer of intraframes is decoded. When human viewing is needed, the decoder would decode the enhancement portion as well, then reconstruct the full intraframe, and then the remaining frames in the GOP are coded predictively using the HEVC pipeline that was extended using a neural network-based frame prediction. So human viewing operates at a full frame rate. So the structure of the decoder is shown here on the right, and most of the coding loop comes from the HEVC pipeline, but this pipeline has been extended using affine transformation-based deep frame prediction here that basically takes two decoded reference frames and predicts another frame, which can then be used either directly as a prediction of the current coded frame without any further motion information, or it can be used as a virtual reference frame in the decoded picture buffer. And in that case, some additional motion might be used. So basically at the encoder side, the particular mode in which this synthesized frame will be used gets decided based on rate distortion optimization, and other components in this coding loop come from the conventional HEVC pipeline. So here are some quantitative results for this two-task codec. Table on the left corresponds to the all intra-coding case, where we test both detection in the base layer of intraframes and reconstruction of those intraframes. And then the table on the right corresponds to the random access case, which involves interprediction, so that's only relevant to the input reconstruction task, namely human viewing. So in the table on the left, note that detection has been tested on the same test set as reconstruction using this SFU HW dataset that's also used in MPEG VCM. It's basically a dataset of object labels and bounding boxes for the common HEVC test sequences. And so this allows us to test both tasks on the same dataset. So if we look at the performance of bit rate versus MAP for object detection, what's shown here in the first column are the BD rate results relative to the HM1620 anchor. And we'll see that there are gains of up to 20% savings in rate compared to that anchor on this dataset. If you look at all the sequences together, the gains are a little bit less, about 14, but in class E, HEVC does exceptionally well, and so without that particular class of sequences, the gains are higher. There are also gains against the VTM 10.0 anchor, and in fact these gains are higher than against HEVC, which seems to indicate that the kinds of artifacts that VVC introduces are not very machine friendly. So as expected, in a way, we get reasonably good gains in the base layer of this system on the machine vision task. We also observe gains in input reconstruction when the quality is measured in terms of MS-SSIM. So up to about 18-19% gains over HEVC. And there's slight loss against VVC, but only a few percentage points. And that's also kind of known because these trainable codecs tend to do quite well on metrics like SSIM. Now, in terms of PSNR, there are of course losses against both HM and VTM. When we look at the random access case, so involving interprediction, we still have gains over HEVC in terms of SSIM, but loss in terms of PSNR against both HEVC and VVC. So let's focus on the comparison against HEVC. We saw that in terms of machine vision bit efficiency, the two-task system achieves gains in this case, whereas in terms of human viewing bit efficiency, there are losses, at least when viewing quality is measured in terms of PSNR, not in terms of SSIM, but in terms of PSNR. So whether or not this two-task system will be useful when compared to HEVC ultimately comes down to the question how frequently human viewing will be needed. So to quantify this, we came up with this notion of a break-even point. So we see that when human viewing is needed, there is a about 9% increase in bit rate compared to this anchor. And so that corresponds to this term in the equation where T sub h is the fraction of time that human viewing is needed. Whereas when machine vision is needed, there are about 13.5% bit gains, and so that corresponds to this term here in the equation. So gains are achieved so long as the left-hand side of the equation is less than 1. And so the value of TH at which the left-hand side becomes equal to 1, that's what we call the break-even point. And the illustration is here in the animation on the right, which kind of shows that your bit savings get reduced as the fraction of time that human viewing is needed increases, and at some point you end up having overall net bit increases. So computing these break-even points against different anchors, we'll see that, for example, against HEVC, when quality is measured in terms of MSSSIM, the break-even point is 100%. In other words, a human can view the video all the time, and it's still the case that this two-task system achieves gains, and that's quite obvious because it has gains both in terms of this column and this column. In case of PSNR, which is the explicit equation shown here, the break-even point is about 60%. The most challenging case is the comparison against VVC in terms of PSNR. But even in that case, the break-even point is about 31%. So long as human viewing is needed less than 30% of the time, the two-task system still provides gains. And so that's quite encouraging for applications that don't require frequent human viewing. So here's another recent system for multitask video compression called Human Machine Friendly Video Compression. And so in this case, features are extracted from input frames and then encoded using a trainable codec, and that forms the so-called semantic bitstream, or what we called earlier the base layer bitstream. And at the decoder, those are then used for visual analysis. Meanwhile, those features are decoded, and then together with previously decoded frames, they're used for frame prediction, and then frame residuals are also encoded here and sent as the so-called signal bitstream, or in what we would call enhancement bitstream. And at the decoder, they then support human viewing. So in the paper, the authors consider two tasks for the base layer: action recognition and object detection, and the enhancement, of course, here is input reconstruction for human viewing. So those were the two recent kind of works on multitask video compression. The literature in this particular area isn't as rich yet, but more studies are in the pipeline, and so this is a kind of an exciting new research area. So we can now take a short break for questions. In multitask video compression, we saw that it's important to code video features. And when it comes to coding video features, a natural question is what happens with the motion in the feature space. So that's what I'd like to talk about next, the latent space motion. And to illustrate a point, we're showing here on the right an image which is one channel of a feature tensor extracted from the add3 layer of ResNet 34. And the question is, what do you think was shown in the original input image? What does this feature channel correspond to? This is not easy to answer just by looking at this feature channel. It seems a bit abstract. But if we were to play the video of this channel extracted from the input video, then it becomes a lot clearer what the input was. And the input in this case is showing wind turbines. And so we see that motion is quite well preserved in the latent space, even if spatial details do not make it easy to tell what's going on. So the question is why? Why is motion in the latent space well preserved compared to the input motion? To help understand latent space motion, we can pose the problem in the following way. If we look at two frames from a video and imagine passing each frame through a front end of a vision model to obtain a certain feature tensor, then if we know the relationship, the motion relationship between these two frames, we can ask the question about what is the corresponding relationship between these two feature tensors. We will use optical flow to model input space motion. Optical flow is usually formulated in terms of this partial differential equation, where I is the input frame intensity, x and y are spatial coordinates, and t is time. And solving this equation for Vx and Vy gives us the optical flow vector at a particular point in the input frame. And the question is, if this equation represents motion in the input space, what is the corresponding relationship between the related feature tensors? To answer that question, we will try to examine what happens to the optical flow equation as it passes through the various processing operations that are commonly found in convolutional neural networks. So those will be the operations like convolution, nonlinear activation, batch normalization, various forms of pooling. And we'll see what happens to the result of that operation and how it relates to the input partial differential equation. So let's start with convolutions. And let's imagine passing an input image I through a convolution kernel F to obtain F convolved with I. We can ask a question, what is the optical flow of that result of the convolution of the input image with the kernel? To see what the optical flow is, we set this PDE for that output F convolved with I, and this equation will result in a new optical flow field, which we denote U sub x, U sub y. So that's the solution of this equation representing flow in the output of the convolution. Now, if we realize that convolution and differentiation are both linear operations and they commute, we can rewrite this PDE here like so. Just pull out the convolution kernel out, and we see that what remains in the bracket here is in fact the same equation, the same flow equation that existed for the input image, because it only now involves I, not I convolved with F. And so what that means is that input flow field is one solution of this new flow equation, because if you make these terms in the bracket, if you make this sum equal to 0, that will also correspond to one solution of this new optical flow equation. So basically we can conclude that the input flow is one solution of the latent flow after passing one convolution. Next, let's see what happens after nonlinear activations. So again, we can ask a question: what happens to the input flow as the signal passes through a nonlinear activation? And to answer that question, we set up the following equation where now we use sigma to denote this nonlinear activation. So this is the PDE describing optical flow after the nonlinear activation has been applied to the input, and the new flow field is u sub x, u sub y. So this time, using the chain rule of differentiation, we can in fact pull the derivative of the activation outside of this bracket, and again we see that what remains in the bracket is the same flow equation that existed in the input, and again the same conclusion applies. If you make this term in the bracket equal to 0, that provides one solution of the new flow equation. So the flow before nonlinear activation is one solution of the flow after nonlinear activation. So using similar type of analysis, it can also be shown that the optical flow tends to be approximately preserved through other operations that are commonly found in convolutional networks, such as pooling or normalization. It should be noted that pooling with a certain spatial scale change will cause a corresponding scale change in the optical flow. For example, pooling with a 2x2 window will cause the flow field to be scaled by a factor of 1/2. But overall, this approximate preservation of optical flow is what makes motion in the latent space so similar to the motion in the input space, even if spatially we don't see as much of that similarity. And this also justifies using common input space motion techniques such as optical flow estimation or block-based motion estimation and compensation. It justifies their use in the latent space as well for feature coding. So at this point we can take another short break for questions. So the next topic I'd like to touch upon is privacy. In most multitask systems, we code features rather than the input directly. And sometimes it's said that because we code features rather than the input, the system is more privacy friendly. But is that really so? Are features privacy preserving? What we see here on the right is an example of trying to reconstruct an input image from the features of the YOLO version 2 backbone. So the top row here are the original input images, and subsequent rows show images reconstructed from various points along this backbone. The reconstruction is accomplished by the so-called mirror model, which basically mimics the structure of the front end of the network, but replaces every convolution with a transpose convolution, every pooling operation with upsampling, and so on. So it kind of tries to invert whatever the input has done. And we can see that from various layers we can still reconstruct reasonable approximations to the input images. To be sure, the deeper we go, the quality of the reconstruction degrades, and that's simply the data processing inequality at work. But some level of reconstruction is still possible even from these intermediate features. And this shows us that features on their own are not necessarily by themselves privacy preserving. We would need additional strategies to achieve privacy, and of course it'll be useful to have a more precise definition of what privacy is. So some of the strategies for privacy that have appeared in the literature are things like adding noise to features, or information theoretic privacy, or resilience to model inversion attacks. So model inversion is exactly this process of trying to recover the input from some features inside the model. And among these, adding noise is not very compression friendly. That would obviously increase our bit rate. But we'll see that the two other principles can in fact be used in conjunction with compression. So the first privacy strategy that we're going to talk about is this so-called privacy fan. And this is a post hoc information theoretic privacy model for multitask compression. So what post hoc means in this context is that this privacy fan is applicable to compression systems, whether handcrafted or trainable, that have been developed or trained without any notion of privacy. And once the system is fully trained and frozen, then it is possible to apply this privacy fan to it to make the system more privacy friendly. Information theoretic here means that the notion of privacy is expressed in terms of mutual information. So the setup is as follows. We have an input here, x, which is mapped to a number of features, here y1 through yc, from which then multiple tasks are accomplished. And some of the tasks reveal private information, and so those tasks will be collected in the set P, the set of private tasks. And others outside of this set are considered to be non-private tasks. And the goal here is to identify a set of features that carry minimum information about private tasks while providing sufficient information about non-private tasks. And the way that's accomplished is by setting up an optimization problem where the mutual information between features and private tasks is minimized, while the mutual information between features and non-private tasks is kept at a certain level that is deemed to be sufficient to accomplish sufficient accuracy of those non-private tasks. So it's an optimization problem whose goal is to identify this set B of features that kind of satisfy this logic. And it can be solved using Lagrangian methods by formulating a Lagrangian that's applicable to each of the features. So Lagrangian for feature I is the sum of mutual informations of that feature relative to private tasks minus some scaling factor, Lagrange multiplier, times the sum of mutual informations of that feature towards non-private tasks. And because the goal is to sort of minimize the sum of all Lagrangians here, it's sort of easy to see that the solution is to collect all the features whose Lagrangians are negative into this set B, because that would basically kind of minimize this left hand side here. So now a special case that's very relevant in practice is slightly different, because oftentimes the number of features that you want to keep in this B is fixed. And so there's a version of this problem where the size of set B is also constrained, but it can also be solved using Lagrangian methods. So let's see how Privacy Fan could help us accomplish that we can call scalable privacy. So the example here is related to a 3-task model, which we've mentioned before. It's trained on the Cityscapes dataset, and the 3 tasks are semantic segmentation, depth estimation, and input reconstruction. And among these 3 tasks in this example, task 1, segmentation, and task 2, depth estimation, are considered to be non-private, whereas task 3 is considered to be private, input reconstruction. So we can then formulate a Lagrangian for each of these features that need to be compressed here as follows. So the private task is the third task, input reconstruction. So the Lagrangian looks like the mutual information between the feature and the third task minus the sum of mutual informations related to non-private tasks, which would be task 1 and task 2 here. And once such Lagrangian is formulated for each of the features that need to be compressed, then using the privacy fan we can collect a set of features that are kind of mostly non-private. In other words, they carry minimum information about private tasks while allowing non-private tasks to be accomplished at a certain level of accuracy. And we can call these base features. So now that we have identified base features in the feature tensor that's about to be compressed, we can then apply fairly light compression to base features in order to preserve that information that is mostly related to non-private tasks, and then we can apply stronger compression to other features, which we call enhancement, and those will be the features that mostly contain information about private tasks. And by varying the strength of this compression, we can control how much of that private information we reveal. So let's see some results. These graphs here show kind of bit rate or file size versus task accuracy, and the first two graphs correspond to the non-private tasks, segmentation and depth estimation, and along the horizontal axis we have a kind of average file size of images in the test set, and in these cases the base layer is fixed and only the enhancement layer is given more or less compression, so that's what varies the rate. And we can see that as we vary the amount of compression applied to this enhancement layer, the accuracy of the non-private tasks doesn't change much. It kind of stays pretty much constant, which sort of tells us that there isn't much relevant information for the non-private tasks inside of that enhancement layer. We've managed to kind of isolate it into the base layer. And then the third graph here shows the file size versus character recognition accuracy in these images. So these images are represent traffic scenes, and in some of them license plates are visible, and so we can consider this task of recognizing characters in a license plate as being a private task, and so it makes sense to examine quantitatively the accuracy of character recognition as the enhancement layer compression varies. And notice that file sizes here are higher than in these two graphs, and that's because these tests can be obtained and were obtained on lower resolution images where fairly accurate segmentation and depth estimation is still possible, but virtually no characters could be read in low resolution images, so we had to increase the resolution of images up to the full size, and correspondingly file sizes were higher. But the compression of enhancement features varied in the same way as it did in these two previous graphs. And we see that how much you compress these enhancement features has a big effect on the character recognition accuracy at this point, where essentially it's mostly only the base layer present in the file, in the bit stream. Virtually no characters can be recognized. But then as you allow more and more bits into the enhancement layer, character recognition accuracy increases, and that's what allows you to sort of scale this amount of privacy, if you will, using the compression of this enhancement layer. And some of the visual examples are shown here. So this leftmost image corresponds to mostly the very highly compressed enhancement layer, so mostly the base layer features, the ones that correspond to non-private tasks, are present here, and this is the kind of reconstruction of the input image that's possible from there. So you can still see that you can see the objects here, the road and so on, but license plates are completely obliterated, so nothing can be seen there. And as you allow more and more bits for the enhancement features, you get to a point where a reasonably clear picture of the license plate is possible, and character recognition accuracy increases. Meanwhile, in all of these figures, segmentation accuracy and depth estimation accuracy is about the same. So enhancement features don't affect those non-private tasks. So another privacy strategy would be to improve the resistance against model inversion attacks. And one way to do that is to develop an autoencoder whose purpose would be to retain information in the features necessary for accomplishing the task while removing information that's needed for input reconstruction. So here's one example, starting with a pre-trained YOLO backbone. An autoencoder is inserted at some point in the this object detection pipeline, and it's being trained to maintain object detection accuracy while reducing the ability for the input reconstruction to be accomplished from these bottleneck features. Once the autoencoder is trained, the bottleneck features could be encoded either using conventional methods or learning-based methods. And throughout this process, the backbone itself doesn't need to be retrained, it's frozen. So this is also a kind of a post hoc method. So two loss functions are used in the training. One is the input reconstruction loss, which in this case is some combination of the quality of input reconstruction. This particular case, it's L1 norm of the difference between the reconstructed input and the actual input. And then another loss term whose purpose is to focus the degradations towards certain areas of the input. And what's being used here are the Sobel operators. So the idea here is that the loss will be focused near the edges of the input image. This loss is applicable at the reconstruction output. So in other words, at the decoder that's trying to reconstruct the input from the autoencoder's bottleneck features. There is another loss, which is the autoencoder's loss, that's composed of the object detection loss and then the negative of the reconstruction loss. So autoencoder is trying to preserve object detection accuracy while minimizing the ability to reconstruct the loss. So here we see that essentially the decoder should be trained with a positive version of the reconstruction loss because it's trying to do the best it can to reconstruct the image, whereas the autoencoder should be trained with the loss term that's a negative of the reconstruction loss because the autoencoder is trying to remove that ability to reconstruct the input from the features. So that leads us to adversarial training. And so the training alternates between training a decoder using this top loss and then training the autoencoder using this combined loss. So let's see some visual results. The two images on the left are the original input images here. The images in the second column are those reconstructed from YOLO version 5's own features without the autoencoder. And we can see that they are slightly degraded because of data processing inequality. Some information has been lost in that initial portion of the YOLO version 5 pipeline. But we can still distinguish, many of the letters here in the top image, and kind of the faces and facial features are somewhat similar to what they were in the original image. And the last column shows the images reconstructed from the autoencoder's bottleneck features. And now we can see that it's very hard to distinguish letters here in the top image, and then facial features and facial expressions are much harder to recover compared to the original image. So those results were obtained without any further compression of the features, and here are the results obtained with feature compression. So the graph on the left shows object detection accuracy in terms of MAP against the bit rate, and the green curve is the anchor, which is in this case compression of YOLO version 5's own features using VVC, whereas the red curve is the method that involves the autoencoder. So compression of autoencoders bottleneck features using VVC Intra. And we see that, as expected, there is a bitrate gain at the same detection accuracy, and that is in part due to the fact that autoencoder's feature dimensionality is lower. The curve on the right shows MAP again, but this time against the PSNR of the reconstructed image. And this is actually what shows privacy gains, because we see that at the equivalent detection accuracy, the autoencoder has been able to reduce the ability to recover the input image, so improved resistance against model inversion. And we also saw that drop in image recovery ability is mostly concentrated near the edges, where a lot of private information is. So we can now take a break for questions, if any. And in the final part of the tutorial, I'd like to talk a little bit about the current standardization efforts that are related to multitask image and video compression. In particular, we will briefly talk about JPEG AI and MPEG VCM, video coding for machines. So the scope of JPEG AI is to create a compact, compressed domain representation that's targeting both the default task, input reconstruction for human viewing, as well as enable effective performance on other image processing and computer vision tasks. And so the main differences, if you will, compared to earlier image coding standards is that it's going to be learning based and support multiple tasks. So not just input reconstruction, but other tasks as well. Some of the use cases for JPEG AI are cloud-based image storage and management, visual surveillance, autonomous driving, live monitoring, and so on. This is a high-level overview of the JPEG AI coding framework. The encoder consists of a transform, quantization, which creates quantized latent representation, which is then entropy coded. And on the decoder side, after entropy decoding, we have multiple options for the decoders. The central branch performs the standard task, reconstructing the input image. The top branch is for various image processing tasks, and the bottom branch for computer vision tasks. The examples of image processing tasks considered within JPEG AI were super resolution denoising, low light enhancement, exposure compensation, inpainting, and so on. And for the computer vision tasks, things like image classification, object or face detection, segmentation, and so on. What's highlighted in green are the tasks that were listed in the JPEG AI call for proposal as optional tasks. So the default task, input reconstruction, was mandatory, whereas these other tasks were encouraged but not really mandatory at the call for proposal stage. And here are the results of the JPEG AI call for proposals. 10 teams submitted contributions based on the call for proposals, and they were compared in terms of several quality metrics, which included PSNR and some of the perceptual metrics, against JPEG 2000, HEVC Intra, and VVC Intra. And we see that all the submitted contributions were better than JPEG 2000, many of them better than HEVC Intra, and a few of them better than VVC Intra. And in fact, several of them had about 30% BD rate gain over VVC Intra. So that's quite encouraging. Having learning-based techniques have this much advantage over VVC Intra, which is the current state-of-the-art handcrafted image codec, under highly controlled conditions. So the proposals of the top two teams here were taken to construct the verification model under consideration, and that's sort of the current point where the JPEG AI standardization effort is. So this verification model under consideration is being finalized. The idea is that the next stage of development will be the collaborative stage, where this verification model will be improved, and if all goes well, the new standard is planned for April 2024, but already within a year, October 2023, a draft standard should be available. MPEG VCM is a related standardization effort for video, but with a slightly different emphasis. So here, just like JPEG AI, the goal is to create a compressed representation from which multiple tasks can be performed, but kind of the main requirement here is coding for machines, whereas coding for human consumption is kind of considered as a optional task. The use cases for VCM are similar to the use cases for JPEG AI. They include surveillance, intelligent transportation, smart cities, many of the IoT type applications. Examples of the various tasks considered within MPEG VCM include both image processing tasks such as enhancement and multi-view processing, as well as computer vision tasks such as object detection, segmentation, tracking, anomaly detection, and so on. Again, what's shown in green are the tasks that were studied in more detail and for which some datasets and testing procedures are recommended within MPEG VCM. These are the machine vision tasks under consideration in MPEG VCM. So we have object detection, instance segmentation, and object tracking. And for each of these tasks, a certain backbone is the focus of the work. And there are a number of data sets and evaluation metrics that have been agreed upon to give a sort of structured framework for evaluation. The work in MPEG VCM has been divided into two tracks. So track 1 deals with feature extraction and compression, where the focus is purely on machine vision tasks. That track runs a little bit slower, and it's currently at the call for evidence stage, which was issued in July 2022, and the response to CFE is expected in October 2022. Track 2 deals with compression for both human and machine vision. So it does include this default input reconstruction tasks. And it runs a little bit ahead. So call for proposal was issued in April, and the response is expected in October. And here are some of the high-level coding pipelines that were under consideration in MPEG VCM. So the pipeline at the top is the current conventional approach, where the video is encoded and then decoded, and the reconstructed video is fed to the machine vision pipeline for further analysis. The next pipeline corresponds to feature extraction and coding. So the initial portion, the front end of the vision pipeline, is used to extract features. Then those features are what's being encoded and then decoded, and then decoded features are fed to the back end of the pipeline to complete the analysis. And then the third pipeline at the bottom is explicitly intended both for machine and human vision, And so there is a feature coding branch that sort of mimics the second pipeline, and that's intended for machine vision. And then there is also a video coding branch, which is intended for reconstructing the input and then subsequent human viewing. And here's a quick summary of what we've learned in this tutorial. The first thing is that multitask compression is not new. Problems related to multitask compression have been in the literature for quite a while. However, there are some new very exciting developments and techniques, and that may be what makes this area so attractive now. Also, some of the requirements of multitask compression are new. For example, the requiring lower bitrate for machine vision tasks. In the past, it wasn't clear that this could be achieved, but now we have both theoretical justifications as well as plenty of empirical evidence that this is indeed possible. Other things that we've learned here is that features produced by neural networks are more compressible than the input, both in the lossless case and in the lossy case. Also, learning-based techniques provide a good way for distinguishing what is relevant for machine vision versus other information, let's say human vision or input reconstruction. So learning-based techniques provide a nice unified framework to do both compression and analysis. Privacy is an open challenge. We need better and more precise definitions of what privacy actually is, and there could be many definitions of privacy depending on what particular aspect we're looking at, and we need agreed upon ways to quantify it in the context of multitask compression. And then we've also touched upon recent ongoing standardization efforts related to multitask compression, such as JPEG AI and MPEG VCM. So both are currently underway. Within a few years, we will have new compression standards that support multitask compression, and then a number of new products will be coming out. So this is really an exciting time to be in this area. So thank you for listening. I hope this was interesting. I hope you've learned something, and I'll be happy to take any questions.